Hello friends, welcome back. Now, in the last class, what we had started about the how the you can handle your data. Uncertainty in measurement is there. So how do you handle your data? How you convert your numbers into your data into scientific notation, how addition, subtraction, division, and multiplication can be done of the numbers which are in scientific notation. We have studied about what are significant figures and what is precision, what is accuracy, and what are the rules for determining the significant figures in your experimental data. In today's class, which is the part 4 of some basic concepts of chemistry, we are going to discuss about the laws of chemical combination. Basically, there are various laws that were being proposed by different scientists at different point of time, at different point of eras, and they basically concern with how the element, and they basically explain that how the elements they combine to give you compounds, in which way, in which composition, in which proportion they are going to combine to give you the compounds. So basically, laws of chemical combination, they explain the combining capacity of the elements to give you the compounds. How they are going to do it, in what ratio they are going to be present, how they are going to combine so that they give you the products. Okay, so there are basic 5 laws that were being given by different scientists. And first law that we are going to discuss over here under laws of chemical combination is law of conservation of mass. The law of conservation of mass was given by Antonio Lavoisier in 1789. And this law of conservation of mass you have studied in your class 10th while you were learning to balance the chemical equations. So why you actually need this law is, this law basically helps you when and it describes why you need to balance your chemical equations. So this law states, basically it states that the mass can never be created nor be destroyed during a chemical reaction. That is, whatever is the mass of the reactants, the total mass of the reactants and the total mass of the products remain the same during a chemical reaction. This was the law of conservation of mass. For example, I have carbon which reacts with oxygen to give me carbon dioxide. Now, the mass of the one atom of carbon is 12 grams. Mass of oxygen molecule is 32 grams. So 12 plus 32 is 44 grams. The mass of the product CO2 that is also formed is 44 grams. So here the total mass of the reactants, which is 44 grams, is equals to the total mass of the products, which is 44 grams. Thus, uh, every chemical reaction, when we balance it, why we balance it? Because it has to follow law of conservation of mass. So every chemical reaction follows the law of conservation of mass, and it has to follow law of conservation of mass always. This what Antonio Lavoisier said in 1789. And I can also write this state, or I can also say this statement as that the mass of the matter can never be created nor be destroyed during a chemical reaction, because whatever carbon, oxygen, carbon dioxide that you are taking, or anything that you take in during in a chemical reaction, that is nothing but a matter. So I can say that the mass of the matter does not change. It does not change when reactants combine to give products. It remains the same. So this is law of conservation of mass. The second law was law of definite, sometimes we also called as constant proportion or composition. So law of definite proportion or composition this law was given by Joseph L. Proust after Antonio Lavoisier gave the law of conservation of mass. After some years, Joseph L. Proust came out with a second law called as law of definite or constant proportion or composition. Now, actually, before starting with the statement, Joseph L. Proust was actually at that time when he gave this law was working on synthesis of copper carbonate. Okay, so he was in laboratory, he was synthesizing copper carbonate, and he found out that the amount of there would be 3 atoms that would be present, or 3 elements that would be present in copper carbonate, that would be copper, carbon and oxygen. Okay, so when he was synthesizing in laboratory, when he was synthesizing copper carbonate, he found out that the percentage of copper is 51.7%. The percentage of carbon in copper carbonate that he had synthesized was 39%, and the percentage of oxygen in copper carbonate that he had synthesized was 9.3%. When he went and he extracted copper carbonate naturally from natural origin, he found out that the percentage of copper is same as that he has synthesized in that copper carbonate, which was 51.7%. Percentage of carbon is also same, 39%, and percentage of oxygen atom is also same, which is 9.3%. So then he gave the statement, which is the law of definite proportion now, that a given compound always contain exactly the same proportion of elements by weight irrespective of the source. Irrespective of from where you are getting that compound, it does not matter. But irrespective of the source, the compound is always going to contain the same proportion or the same amount of elements by weight. Their masses, the elements masses would remain the same irrespective of the source from where the compound has come. Let's, for example, I give you another example. Let's say I have water. Now water, if let's say I've taken water in a beaker which is a sea water, I've taken another beaker and I've added rainwater to it. I've taken third beaker and I've added tap water to it. Now water will remain water, which is H2O. That is, in each case there would be two atoms of hydrogen, one atom of oxygen. That means that the masses of hydrogen is to oxygen, that is 2 is to 16 or 1 is to 8, will remain the same for each of the case. Does not matter whether it is a sea water, does not matter if it's a rainwater, does not matter if it's a tap water. So the masses of the elements will remain the same. The ratio of the masses of the elements will remain the same in a particular compound as long as as long as we are talking about the same compound. So the same compound, if we are talking about, then the masses of their elements ratio will remain the same. Now, this is a numerical which is based on law of definite proportion, which is there in your NCERT, and it says that in an experiment, 0.243 grams of magnesium on burning with oxygen yield 0.4030 gram of magnesium oxide. That is, there was some experiment in which magnesium was burned with oxygen to give magnesium oxide. And how much magnesium was burned? 0.243 grams magnesium was burned to give 0.4030 grams of magnesium oxide. So, we all know through mass of conservation of mass law that the total mass of the reactants is equal to total mass of the products. So, the mass of oxygen would be the mass of magnesium oxide minus the mass of magnesium, which is 0.160 grams. Okay. Now, in another experiment, in the second experiment, 0.182 grams of magnesium burning with oxygen yield 0.302 grams of magnesium oxide. Okay. So, in second experiment, what happened? Some amount of magnesium was burned with oxygen to give magnesium oxide. So the mass of magnesium that was burned was 0.182 grams and it yielded 0.302 grams of magnesium oxide. So mass of oxygen would be mass of magnesium oxide minus mass of magnesium, which is 0.120 grams. Now let's take, now I have to prove that the data, in each of the experiment, the data follows law of definite proportion. That means the ratio of the two elements, magnesium and oxygen, in experiment number 1 and the ratio of the elements magnesium and oxygen in experiment number 2 yielding two different masses of magnesium oxide should be same. Okay, so magnesium is to oxygen mass, if we take a ratio, it would be 3:2. Here also, if I take magnesium is to oxygen masses, it would be 3:2. That means the data that is given to us follows law of definite proportion. It does not matter that you have done experiment number 1 or you have done experiment number 2, the ratio of the elements by their masses will remain the same, because magnesium oxide basically is made up of magnesium and oxygen. So if you have done experiment number 1 by they're taking different mass of the magnesium and oxygen and you have got magnesium oxide, so the mass of the elements magnesium and oxygen is 3:2. Similarly, if you have done experiment number 2 also, if you have taken some other experiment, you have done experiment number 2 and you have taken some other mass of magnesium and oxygen, and still the ratio of magnesium is to oxygen would remain the same, which is 3 to 2. So it does not matter if you do experiment number 1, or it does not matter if you do experiment number 2, you are getting magnesium oxide, and the ratio of the masses of the element in magnesium oxide, that is magnesium is to oxygen mass, will remain the same whether you do experiment number 1 or you do experiment number 2. The third law that was being given by Dalton in 1803 was law of multiple proportion. And the law of multiple proportion says, before the statement, let's understand what is law of multiple proportion states. Let's say I have hydrogen, I have oxygen, it gives me H2O. But hydrogen and oxygen can also combine to give me hydrogen peroxide, H2O2. Now, 2 grams of hydrogen reacts with 16 grams of oxygen to give me 18 grams of water. And 2 grams of hydrogen reacts with 32 grams of oxygen to give me 34 grams of hydrogen peroxide. Now, this law actually says that when 2 or more elements combine, that is 2 or more than 2 elements combine to form more than one compound, that is once it is forming H2O, in the other case it is forming H2O, so it is forming more than one compound. The masses of one element, the mass of one element that combines with the fixed mass of the other element bear a simple whole number ratio. That is, the mass of one element that combines with the fixed mass of the second element bears a simple whole number ratio. That is, in both the cases, the mass of hydrogen is fixed. So, the mass of oxygen is varying. This ratio, that is 16 is to 32, is 1 is to 2. It is a simple whole number ratio. So, law of multiple proportion states that when 2 or more elements combine to give me 2 more than one compound, the mass of one element that combines with the fixed mass of the other element bears the mass that you are changing. This bears a simple whole number ratio. So, here it is 1 is to 2. So, what are simple whole number ratios, which could be 1 is to 2, 2 is to 1, 1 is to 1, 3 is to 5, 5 is to 3. So, these are all simple whole number ratios. But these two elements, they can combine to give me more than one compound, but they will do so in a simple whole number ratio. But it will not happen that the ratio is coming out to be 5 is to 11 or 7 is to 13. No, in such ratio, the elements are not going to combine to give me more than one product. So, the products that you are getting, which will be more than one, will only be possible when your elements that are combining, in which one of the elements mass is fixed, the other is varying, and the element's mass which is varying bears a simple whole number ratio. So, this is the law of multiple proportion given by Dalton. The fourth law was given by Gay-Lussac, and it is called as Gay-Lussac's law of gaseous volumes. And since the name itself suggests that it was given by gases only, so the matter which existed in gaseous form, that for that Gay-Lussac's law is valid, and it was given in 1808. And this law states that when the gases combine or are produced in a chemical reaction, they do so in a simple ratio by volume at a constant temperature and pressure. If let's say some amount of hydrogen combines with oxygen to give me water at a particular constant temperature and pressure, then the volumes of the gases, hydrogen and oxygen volume, should bear a simple whole number ratio. Then only the water molecule would be formed. That is, let's say I have taken 100 ml of hydrogen combines with 50 ml of oxygen gas, then the volumes of hydrogen by oxygen would be 100 by 50, which is 2 is to 1, which is again a simple whole number ratio. So, as long as the gaseous hydrogen volumes has a simple whole number ratio associated with it, then they can combine to give me the products. Okay, so let's say if the volume of hydrogen by volume of oxygen comes out to be 3 is to 11, let's say if it comes out to be, I've taken uh, 3000 ml of hydrogen and 11,000 ml of oxygen. So if you think that it will give some amount of water, no, it is not going to happen, because 3000 by 11,000 is equal to 3 is to 11 ratio, and this is not a simple whole number ratio. So any reaction which is having 3000 ml of hydrogen or 11,000 ml of oxygen will not give me water molecule. That reaction will not take place, be it at same temperature and pressure also. So the ratios of the volume should be simple whole number ratios, then only you will get the products. So actually, basically, if you see, you know the law of definite proportion that we have done, second law, that the masses of the elements were in a simple whole number ratio. Here, the volume of the gaseous elements are in a simple whole number ratio. That is the only difference. Otherwise, in both the cases, the elements, the ratio of the elements should bear a simple whole number ratio. The only difference is there we were talking about masses of the elements of the compound. Here we are talking about the volume of the elements of the compound, and also there it was for the solids and liquids, and this particular law is only valid for gases. So that is the only difference. So basically the Gay-Lussac's law was a special type of law of definite proportion also. Fifth law, which is the last law, this was given by Avogadro, and we will be discussing more about it in your states of matter chapter also. But here this was given by Avogadro, and actually this law states that the equal volume of gases at same temperature and pressure should contain equal number of molecules irrespective of the gas that you are taking. It does not matter whichever gas you take, but if you are taking the volume same, then the number of molecules in that particular gas will also be same at constant temperature and pressure. For example, let's say I've taken one volume of hydrogen in a container, and it contains, let's say, 5 molecules of hydrogen. I'm assuming it. So if I take one volume of hydrogen in a container, hydrogen gas in a container, it would contain 5 molecules of hydrogen. Let's say in another container, I take one volume of hydrogen again. So since one volume of hydrogen, I have said it contains 5 molecules of hydrogen. So this also, here also, because since the volumes are same, the one volume of hydrogen will contain 5 molecules of hydrogen again. In the third container, I have taken one volume of oxygen. Now I know one volume of anything, any gas would contain 5 molecules. So one volume of hydrogen containing 5 molecules of hydrogen, one volume of hydrogen contains 5 molecules of hydrogen. So I know that one volume of any gas is going to contain 5 molecules of that gas. So one volume of oxygen will also contain 5 molecules of oxygen. Now I interconnect these containers, then what is going to happen? The gases are going to come out into the tunnels, and it is going into the interconnecting tunnels, and they are going to react with each other. When they are going to react with each other, let's say I get 2 volumes of water vapor or H2O. Now one volume of the gas contained 5 molecules of the gas, right? In all the 3 cases. Since the volumes are equal, the number of molecules will be equal according to Avogadro's law. Thus, when uh, when one volume of each gas contained 5 molecules of the gas, so since the number of the product side, the number of water molecules that are produced, the volume has been doubled, which is 2 volumes of water vapor were produced. So number of molecules will also get doubled. From 5 it will become 10. So the 10 molecules of water H2O will be produced in the product side. Alright, so Avogadro law just states that when if you are taking equal volume of any gas, irrespective of the gas you are taking, if you take equal, the volume should be equal. If you take equal volume of any gas at constant temperature and pressure, the number of molecules that it is going to contain will remain the same. Okay, so this is what we had to discuss about the laws of chemical combination. The 5 laws, which is the law of conservation of mass, law of definite proportion, law of multiple proportion, Gay-Lussac's law, and Avogadro's law. In the next class, what we are going to discuss would be the Dalton's atomic theory.